Okay, thanks for the kind invitation, and thank the organizers for having me here. So it's really my great pleasure to be here. Okay, so today I'm going to talk about this inviscid limit for this Navier-Stokes equation. So here, that's the inviscid limit for this Navier-Stokes equations. Can you see?
Yeah, that's very nice.
Oh, okay. Okay, cool. Okay, so talking about this topic, I want to mention a famous paradox. It's called the D'Alembert's paradox. So according to his computation, actually the bird cannot fly and the plane cannot fly. That's because according to his computation, the forcing acting on some object moving in the fluid is 0. So the total forcing is 0. Of course, this is a horrible word and it's not real. So in order to resolve this paradox, this Prandtl proposed this Prandtl, and we call it the Prandtl theory. So basically it said that assume here you have this fluid. For simplicity, let's assume the speed of the fluid just a constant, and you have a plate here. Here, this is maybe some plate here. So in fact, for the place far away from this plate, the fluid is just pass by like a constant speed. But near this plate, there's a boundary layer here, and the thickness is like square root of nu, and this nu is the viscosity of the fluid. So here, there's inside this boundary layer, the velocity of the fluid changes dramatically. Here, also included the vorticity. There's like a large vorticity generated near the boundary of this plate. So that's kind of the start point. And then next, let me introduce this. Inviscid limit problem. So here this. So that's I denote IL. So this is for inviscid limit. So talk about this inviscid limit. I need to first let me write down this Navier-Stokes equation. Here, this is the Navier-Stokes equation. dt u s plus u and s dot gradient u and s minus new Laplace Navier-Stokes equation, and then plus the pressure s equal to 0. And we also have this divergence free condition, which means that the fluid is incompressible. And then we impose the boundary condition such that Navier-Stokes equation. For example, we consider this problem in a torus in x direction and the half line in the y direction. So here that's the positive line. So here we impose the boundary condition y equal to 0 is equal to 0. That's the standard non-slippery boundary condition. So here that's the Navier-Stokes equation, and then also have this Euler equation. This Euler equation is very much like this Navier-Stokes equation. Here, that's the Euler equation. Plus u e dot gradient e plus gradient p equal to 0. For the first equation, as you can see, the only difference is this different term. So, and of course, we have this divergence free condition. Here, it's incompressible. And for the Euler equation, the boundary condition is a bit different. Actually, we only impose the non-penetrating boundary condition, which means that the vertical component of the velocity is 0, only the vertical component. So vertical component is 0. So because these two equations are very similar, so a natural question is to ask, like, if you send this parameter nu go to 0, do we have that this Navier-Stokes equation converts to this Euler equation as nu go to 0? I think that's divided here. So here. And if we have this kind of convergence, in what kind of sense? Right. In what sense do we have this?
So we start with the same initial conditions, or?
Oh yeah, we start with the same initial condition, or we can we can let the initial condition of this Navier-Stokes convert to the Euler equation. Yeah. So the inviscid limit problem is asking like this specific limit. So if nu go to 0, you have this supremum of from 0 to capital T. This T is some like positive constant on this time interval. And then this Navier-Stokes equation minus this Euler equation L2 norm. Is this limit equal to 0 or not? And the answer to this question depends on the domain a lot. Actually, when the domain is like, for example, when the domain is torus or the whole space R2, the answer is very simple, and I will give a very simple proof of that case. But when there's a boundary, then this problem is very challenging. So, let me first talk about this domain without this. So this, yes, the answer is yes for the domain torus or R2.
Yeah, I have a question. I was trying to make a connection with the Prandtl picture and the boundary conditions. Is it where is the periodicity coming in, or this is just a sort of example?
Oh yeah, this picture is a general picture. If you really want to consider, you can consider like here. For example, you can consider like here. Let's assume like in this x direction, it's like periodic. And then this plate is inside this like boundary, right? Here, but for this case, I just want to illustrate a little bit this Prandtl like theory. You know, like actually something weird happens near the boundary. Yeah.
And here the sort of this object, the obstacle, is a boundary. You treat it as a boundary.
Oh yeah. You're right. Yeah. Here this in our case, the domain we are considering is this, right? Here this, right? It's kind of like this. That's the boundary. You can consider this just as the plate, right? So here this, the boundary as the plate, and that's the fluid.
And then it's periodic in the other.
Yeah, periodic in this x direction, and in the y direction is the like positive half-life.
So in particular, there will be a layer right near the boundary.
Yeah, when there is a boundary, there should be some like boundary layer here. Yeah, correct.
So the sides are periodic, right? Or
Sides are periodic.
Yeah.
There's no boundary layer there.
Oh, no.
Only the bottom.
Oh, side. There's no boundary layer on this side. It's just this boundary. Yeah. Periodic. And here, like that's for a domain with the boundary. But when there's no boundary, for example, this torus or R2, the problem is very simple. So here, let me. For example, we can assume that the initial data. Let's assume these two equations have the same initial data, and we assume the initial data is like very smooth. For example, H4. Here I'm not doing it in an optimal way, but you can do it. So here I just want to like show you an example. So here this, and if you assume initial data is in H4, then for the Navier-Stokes equation, you have that supremum of, you have the local Wilpost. Actually, for the 2D case, you have global Wilpostness, but let's just focus on this local one. So it's supreme T Navier-Stokes equation. L2 norm is bounded by constant, and this T, this Euler equation L2 norm is also bounded by constant. Then let's denote this. Denote V equals the difference of the two solutions. That's your Euler equation. And then it's very easy to get an equation for this V. So actually, you get the equation for V is dTV plus V dot grad V. And plus this pressure, let me denote this P is the pressure difference of the two pressures. So here, and on the right-hand side, you have that the different term. That's here new Laplace your Navier-Stokes equation, and then you will have this nonlinearity. You subtract this one from this equation. So what you get is you will have like a negative Euler dot grad V, and then you will also have like this V dot grad Euler. That's the equation here. And then what you can do is like here you just do a normal like L2 estimates. So here this f d by dt V to norm. And then for this term is gone because here the divergence free condition, this term is gone, and also this is gone, and also this term is also gone because of the divergence free condition. So here these are all gone. So on the right-hand side, what you have is just new Laplace U Navier-Stokes, and then V minus V dot grad U Euler dot V. And you can have, let's do holder here, L2. So what you get is new Navier-Stokes, L2 norm, V, L2 norm, plus this. You can like put L infinity on this guy because we have enough regularity. So here, L2 norm squared, right? Then our ground estimate, our ground inequality would imply that ground imply that supremum from 0 to capital T, this V L2 norm is converging to 0 as new to 0. This proof is pretty simple. But when there's a boundary here, then the problem becomes like very challenging. The bigger problem is like here the mismatch of these two boundary conditions, right? So here for Euler you allow the fluid to like slip along the boundary, but for Navier-Stokes equation the speed, the horizontal speed is 0, right? So that's the main difference. Okay, so here that's this easy case, and then for the domain with the boundary, we need to work hard. So here that's the limit, I think. And then I'm going to give a brief history of this like inviscid limit problem with the boundaries. So here that's brief history for this inviscid limit problem. The first work I want to mention is by Prandtl. So here there is Prandtl. I think it's 84. So here, his result is more like a criterion for this inviscid limit problem. So he proved that if nu from 0 to t, and then from, let's say, the domain for this integral is a strip like close to the boundary with the thickness of nu here. So let's say not square root nu, but nu. So, and then gradient of the equation dx ds. If this integral, this integral, that's the total dissipation near this boundary. If this limit go to 0, this would imply that you have the inviscid limit.
So is that using an energy estimate like the one you have there or not?
Yeah, they use the energy estimate, but it's a little bit involved. You need to use some a boundary corrector there.
I see.
Yeah, but basically it's the energy estimate. Energy estimate.
It looks like it.
Yeah. And that's this result. Then I'd like to say that's the start point of this kind of like project, and then later on people refine his work a lot. They are sequential papers. And then another breakthrough is due to Sammartino.
Is this Torsio-Kato?
Torsio-Kato, yeah.
He must have been pretty old when he did this.
Yeah, I think so.
Because I was an undergraduate in Berkeley. I knew him then as a professor, so that was a long time ago.
Yeah. Okay, so here this another breakthrough is by this Sammartino and Caflisch. This is 1908. For this breakthrough is like they are not giving some criteria anymore. They prove that if your initial data is analytic, let's see, analytic initial data would imply that you have this inviscid limit problem. And actually, in this paper, what they proved is like they verified the so-called Prandtl expansion. So here, what they prove is like this. They prove that this Navier-Stokes equation is equal to this Euler equation. Here, I'd like to variable here. So this Txy is equal to Euler equation Txy plus this Prandtl equation, Prandtl solution, Txy over square root nu, and plus some term of the order of square root nu. Their approach is like to introduce this Prandtl corrector, and they analyze each of this solution carefully and establish this expansion. And from this expansion, this would imply that you have this inviscid limit. And usually, like to get this kind of expansion is hard. Right? So here. And
what? I'm sorry. What's the Prandtl equation look like?
The Prandtl equation. The Prandtl equation. First, the Prandtl equation is an equation like which would describe the phenomena of this fluid near the boundary.
Layer, right?
Yeah, boundary layer.
So it's somehow it comes from some kind of multi-scale expansion near the boundary.
Yes. The equation is. Do you want me to write?
Yeah. Well.
Yeah, Yeah, I can write this equation down. So here there's the Prandtl equation. Is here there's.
I just don't know it. So yeah.
Oh yeah, it's this Prandtl equation here. Let me omega this p. I do not want to keep tracking. So you know I am talking about this Prandtl equation. Yeah. So dx u plus v dy u minus nu. There is no nu here. This. Yeah, this nu dy yu equal to 0. So actually this not here. I think it's here. So that's the Prandtl equation, and you have this divergence-free condition, which means ux plus v y equal to 0, and this you can put this like no slip boundary condition at y equal to 0. They are 0, but there's a match like you have like there's some boundary condition happens here, right? So where this Prandtl equation meets this Euler equation. So that's the boundary condition is given by this limit y go to positive infinity. This Prandtl equation is equal to this Euler, and then this. Okay, that's good. And yeah, sorry, here I messed up. There's dxp, and this is the Euler pressure. Yeah. Okay. Yeah, that's this Prandtl equation here. This and here this because I already wrote this Prandtl equation, maybe I can talk a little bit more about this Prandtl equation. So here this Prandtl equation is like here, as you can see, like we only have an equation for this u, and there's no equation for the vertical velocity v here. And so you would expect that in this equation, v is recovered from like integrating this u. And here you would expect here this, you would expect x derivative loss in this equation. So that's the main trouble here. This you have x derivative loss. So that's why we expect that actually you need some analytic initial data to recover that derivative loss. But actually people could improve the result a little bit. They prove that actually the Javari class, some Javari class with the exponent high enough could also imply this well-posedness of this Prandtl equation.
So if you do what? If you assume
a Javari class, yeah. Okay, so that's the Prandtl equation, and here, oh yeah, I was talking about this Sammartino-98, and then there's another breakthrough.
Do you want analyticity in V? Or does it matter? Is it analyticity in both directions, or analyticity in some directions as needed? Is it homogeneous analyticity, or there is more smoothness you need in x versus y?
Oh, you mean for this equation, right? Yeah, like this. I think this actually what you want is the x direction analyticity, right? So actually in the paper, in a improved paper, they only assume that you only need the Javari class in x direction, right? But for this kind of equation, like when first establish the well-posedness in the analytic setting, they are assuming like both the direction are analytic. But I think the x direction analytic is already enough. Yeah. Right. And another breakthrough work is due to Miyakawa from this is 2014 work. So this work is a little bit shocking. That's because here in their paper they are assuming this Sobolev initial data, but here they plus some condition, like here this support of the vorticity is away from boundary. It's away from boundary. This would imply that inviscid limit. So here, but if you really think it for a while, you find that actually it's not so surprising. Like that's because here have this, assume this is the boundary, and then that your vorticity is supported away from boundary, right? So it's not touching the boundary, so everything is fine, right? So here the idea is like here, that's supported far away, and after some time, you mean like the vorticity satisfies some transport equation, right? So after some time, let's say that that's the support of the vorticity at time t. So when this time t is not big, not so big, actually you are expecting that the distance, this distance t is still bigger than 0. Right? So the Euler equation, the solution is still, our support is still away from the boundary. So in this case, the corresponding Navier-Stokes equation is like very small. It's very small here. Like, so in other words, like here you have smallness, so there's like no strong interacting between these two parts. So everything works out.
But is it very regular
there? You mean here? Yeah, it's very regular. Actually, they prove that the solution is analytic here.
Okay, so,
yeah, it's analytic. Yeah. And although it's like the intuition is, although the intuition is like kind of simple, but still that paper is also super complicated. So here, let me show you this. Show you a picture of this vorticity. So here, assume this is the y direction, the vertical direction, and then near the boundary, the vorticity is of the size of 1 over square root nu here, right? And then it's like away from boundary, and then the vorticity is like become very small, and then for a while, like when it's like assume that's the support of this vorticity, then after a while, then it's like become like a constant size. The solution is something like this. And here, this is very, very small. So it's the size of exponential 1 over square root nu. It's very small.
What is I'm sorry, what is the picture of?
Oh, it's the vorticity.
Oh,
vorticity, yeah. So here, this is very small here. So it seems like it's kind of like this smallness kind of like cut off the interaction between this boundary vorticity and this bulk flow, right? So here, so when they are not like interacting, then everything works fine. You can have this, like you can have that Prandtl expansion, and you can have this inviscid limit. So
this is for some time t between 0 and capital T?
Oh, yes, yeah. Okay, so here this, and then the problem comes like how about if you, because if you just consider these two results, you will find that actually this analyticity is really only needed near the boundary, right? And then for inside the domain, far away from boundary, you just need the Sobolev regularity. But here the problem comes like.
But even if you have it near the boundary initially, it's analytic. stay analytic? I mean, because you don't have it. I mean, do you have? How do you know that the singularities don't propagate inside pretty fast?
Yeah. That's you're asking the main question. That's the big trouble. Yeah, when they are like meet together, like you may think that it can happen that the Sobolev regularity can destroy the analyticity immediately, right? Yeah, pretty fast. Yeah. So yeah, that's how do you know? And then.
I mean, you have to worry about propagation of singularity somehow. Right?
Yeah, exactly. Yeah. So here, since you talk about this, actually I can mention a little bit. Like here, this in our work we are trying to unify these two results here. These two results. So what we proved is that actually here assume this is the boundary, and then you assume like for a constant strip, like this distance is a constant. Let's say make it 1. So the distance in this strip it's analytic, and in this inside domain you have Sobolev domain, and then
What kind of Sobolev do you allow? I mean, how?
H3. Yeah, H3. Yeah. Sobolev, and then it turns out that the scenario is not too bad if you have like this. If you have this, I would not say it's some like specific initial data. It's like here this. If you assume that the radius of analyticity is like decreasing linearly here. So near the boundary is the radius of analyticity is like, let's say a constant. Let's say mu0. The decrease to 0, and after this point is not analytic anymore. It's Sobolev, right? So then our results show that actually this like Sobolev part is not so bad. It cannot destroy it immediately. Either way, yeah. So actually although the radius of analyticity will shrink.
Yes.
So but it maintains this linear decrease. Like after some time it's here, but this distance is still like of order 1.
It influences it, but it doesn't destroy it. Yeah.
Yeah, it doesn't destroy this. Yeah. Mm-hmm. Here this. Here this. I also want to mention another. Work.
Thing you have to show that this picture is preserved under the time evolution for short time.
Yes, yeah.
Is that the main issue, or are there other issues too?
I would like to say that's one of the main issue here. Yeah, and also, yeah, you need to like consider like how this, you need to consider how this analytic part is evolved, and the Sobolev part is evolved, and also there's another like difficulty here, like this point, At this point, it seems like it's not clear, like whether you should think it like an analytic part or the Sobolev part, right? So here, when these two parts meet, you need to be careful about this analysis. Yeah. Mm-hmm. Okay, so yeah, I also want to mention the work by Angi and Angi. Yeah, that's another work. Here it is. Three. Angi and Angi. I think it's 2018. So their result is like they gave another proof. So basically, they gave another proof of this Sammartino, this result, Sammartino and the they gave another proof, but the really the really elegant part of this paper is that they could avoid this kind of expansion. They avoid this kind of expansion. So here, without this, let's say, Prandtl expansion. And motivated by this paper, so we are trying to unify these two results, this one and also that one, without using these characters. So, okay, so that's about this, the history here. So maybe next I just should I? Maybe I want to leave this equation here. So next, I'll talk about our result and give the key elements in the proof. Okay. Okay, so here is our result. Our result basically is like this analyticity, near the boundary, plus Sobolev inside the domain. This would imply this inviscid limit.
So who's the hour?
Oh yeah. This is I should mention it at the beginning. This is a joint work with. Sorry, I should mention it earlier. Joint work with Igor Kukovic and Vladvico. And yeah, as I explained here, the main difficulty is because actually from this picture it's easier to state the main difficulty. That's because here you don't have this smallness, right? You don't have this smallness, so there are these two parts, the boundary vorticity and this bulk flow, they are like interacting strongly. So in this case, you don't really know like what happens here. So that's the main difficulty. Obviously, like this approach will not work because they use the fact that this should be really small. So okay, so the main difficulty is like to consider where this boundary fluid and this like the analytic part and the Sobolev part they meet. So that's the main difficulty. So here let me give some like key elements. See, key element in the proof. The first thing is the like we need to design the domain. So here that's the first thing. Okay, so here there's the domain is here the strategy is like we want to extend like our our like a real solution to this complex domain, and then we use that analytic strategy, right? So here, this if you just consider this kind of domain here, this. If you just, let's say, fix 2 points and then you extend it like this, you want the function to be analytic in this region and sublevels in this part, it's not good. It's already not good because if you do this, that's the bad thing happens exactly at this point because you don't have enough time for the analyticity recovery. I'll talk about this later. So like, you don't have enough space here, so it will blow up immediately. So instead, we will consider this kind of domain. Here, this is 1. So our domain is here, this one. And then we require this angle to be like 45 degrees. Here. 45 degrees, and the solution is, we assume the solution is analytic in this part and sublevels in this part. And if you define in this way, then here we denote this domain, this angle. If you let this angle to be mu, so we denote this domain to be omega mu. And if you do that, you will find like if you draw a different parameter here, at every point, you have enough space, except at 0 point, but we have conormal derivative, so it's fine. So here you have, like, for each point, you have enough space to do the analytic recovery. Okay, that's the domain, and then then I also need to, I guess I will not talk about this, how to construct this weight function. So here I just briefly mentioned there are some weight function here. So this weight function. Weight function, and it's given in this way. Omega z is equal to square root nu, and from square root nu to 1, it's equal to y, and then it's equal to 1 when y bigger than 1. It's this weight function, the reason why we use this weight function is because we want to capture the phenomenon that the solution should be something like this. We are expecting the solution is something like this. Near the boundary, it's of the size 1 over square root nu. And far away from boundary is like a constant size. So here we want to add this kind of weight function to capture this kind of phenomenon. Right? And there are tons of weight function you can choose, as long as it captures this kind of phenomenon, and also it satisfies some like monotone, some kind of weak monotonicity. Okay, so here this I just briefly talk about this part, and then I'll introduce.
One thing you told me at dinner, but I don't think you said it in the result, is in which sense it goes to, in what norm it goes to the, you have this Inviscid limit?
Oh, it's, it's in this L infinity. Let's say L infinity from time 0 to t, and L2 in this space. Yeah, L2. Mm-hmm, yeah.
And can you do better than L2, or is that
yeah, like here, this for this Inviscid limit problem, like they ask specific in this kind of topology if you have the convergence, right? Of course you can. Yeah, it's a natural one, but you can consider like even you can even consider like L infinity, this kind of thing. I think I would guess like this is it's not easy to get. Yeah, to do this actually I think you cannot avoid the boundary corrector anymore.
I can't.
Yeah.
It seemed like that. You're right.
Yeah. So.
Without a corrector.
Yeah, without a corrector you cannot do that. But our point is like in our paper is like we'll try to avoid this boundary corrector, because if you do boundary corrector, things get like really complicated, kind of auto control. If you want to do L infinity, then I guess you want to some like new techniques,
Yeah.
you know.
Very good, thanks.
Sure. Okay, good. So here this next I want to introduce a norm here. That's the norm. This norm is specifically designed for this kind of domain and this weight function. So here this norm, we define this norm x mu is equal to probably this is the okay. We have actually we have three kind of norm: x norm, y norm, and z norm. X norm is L infinity based norm. Y is L1 based norm, and this is Sobolev norm. And why do we choose?
All spatial.
Yeah, these are all special. Like here, why do we choose these two kind of norm? That's because like these two kind of norm is kind of critical in terms of this vorticity nu, which means that if you send nu go to 0, your data will not go to 0 or blow up. Like it will remain a constant size. Right? So that's this kind of critical norm. So here this norm, these two norms are kind of similar. So I just tell you like how do we define this x norm. So here this x mu norm is equal to this supremum y belongs to this domain omega mu. And then you have this weight function omega y, and then you have this analyticity in x. So it's 1 plus mu naught, 1 plus mu minus y relative c, and then f c y. Here, this f c means that we take the Fourier transform in x variable here. Right? In x Fourier variable. So here that's the x mu norm.
Now, I want to make sure I understand something. Maybe I missed the point. So this picture up here that you have with this is in the complex domain, is it?
Yeah, it's in the complex.
So what do you mean? So this is
Oh,
also
yeah.
in the complex domain.
Yeah, this is also on complex domain. Yeah, you're right. I should mention it earlier. So this y is a complex number. So this y is a complex number. So here it seems like everything you should have like here you should have the real part of y.
Okay.
But because actually if you do the energy estimate, you will find like there's no big difference between this complex and the real variable. So I just pretend that we have this real number. Yeah.
I see. Because your weight is only defined on the real, so
Yeah,
I wasn't
yeah.
sure what you meant when you did.
Oh yeah. Yeah, I should mention this earlier. It's a complex number that here. So for this talk, I just like treat this complex number as a real number. Like it won't make a big difference in the estimate. Yeah. Okay, that's the x mu norm, and then we define this. We define this x norm in the following way. So here this x norm is equal to this. We take a supremum of this. This gamma is a big constant. We will treat it later. So gamma t is less than mu naught is some constant. That's the radius or the analyticity for the initial data, mu naught. So here supremum and then supremum of mu less than mu naught minus gamma t. And then you have this. That's the first derivative. So it's dxi. We use, in the whole paper, we use this conormal derivative here, y dy j, and the f x mu naught, and plus this second derivative. For the second derivative, it's a little bit different because we need to recover one derivative. So in this case, you need some like weight function. I'll talk about this. How do we use this kind of function to finish that analytic recovery part? So here there's a weight function here. So it's mu naught minus mu minus gamma t to the power of half plus alpha. Alpha is any positive number, not too big. Let's say close to 0, but it's some positive constant. Right. So here this dxi y dy to the power j f x mu naught. That's the x norm. And here this weight function is really like the key point to do this analyticity recovery here. So, and that's the L infinity base norm, and you can similarly define this this y norm. This L1 based. I think I messed it up somewhere. So here this x norm, you take the Fourier transform and then it's L1 in C. I thought something is bothering me. So here that's L1 in C. Some L1 in C and L infinity in the y variable.
Sorry, what are you saying?
Oh, this norm, it's L1 in C. It's like this. Okay. This is the C mode, right? Yeah. So you sum them up.
Fourier transform.
Yeah, Fourier transform. Yeah, you sum them up. So here, and then that's the y norm, and then Sobolev norm. You just use the usual Sobolev norm with weight, like a y weight, and not more. So here there's the Sobolev norm, and then that's the norm of. And then I think I just maybe I should have stayed here. About this analyticity recovery part, it's like here there's analyticity recovery part. It's like basically it's like if you look at an analytic function, let's consider the complex function. If you look at then you have like, let's assume like you have a ball that's with radius small r, and then supremum of the derivative of this function, it's less than 1 over capital R supremum this with a big ball with the radius capital R, and then f z. That's the main the main intuition about this in analyticity recovery part. So here I just illustrated for like analytic function. Of course, for the norm, you need some work to show the corresponding this kind of estimates. But that's the main intuition actually is here. So actually, if you look at this, the main thing about this kind of recovery is like here we can sacrifice some space, but the upshot is like we can gain one more derivative here, right? So right here. So actually, if you
so this is where you have to use analyticity very, very heavily. I guess you can't get by with Givray or anything like that. Is that right?
Yeah. I think the Givray. I think there's no.
Without you can't. There's no results like the Caflisch one with Givray.
No such thing like that. Yeah, it's because as you can see from the Prandtl equation, it's really natural to use the analytic to recover by derivative, right? So here I mentioned this analyticity. You need some enough space. That's what I mean. Like here, if you have enough space, right? At any point you have enough space, you can recover one derivative at any point, right? That's the main idea.
So then do you use a kind of energy estimate with these norms, or what?
There's kind of run out of time. So I guess I just finish it with a very very brief estimate. So I just give you a flavor of the estimate because it's super complicated. Not super complicated, but it's not like straightforward. I cannot give much detail here. So let me just tell you what we need to do. So here, actually, if you look at the equation, we consider the vorticity formulation of that Navier-Stokes equation. So it's like this one, you got omega, and then with some kind of weird boundary condition here.
Oh yeah.
This omega is equal to negative dy plus inverse du dot gradient omega at the point y equal to 0. Yeah. So that's
the boundary condition.
Yeah, that's the boundary condition. And for this kind of system, we want to use the wider formulation. So here we have a green function for this system, and the green function, the green function is estimated in the paper by Angi and Angi. So we could just borrow the estimate there. So actually we have this mild formulation of this, for example, this initial data term, right? And plus this forcing term, it's like from 0 to t and from 0 to infinity, and then we're considered in the Cauchy mode. So here it's green function g Cauchy t minus s y minus z, and then you have the forcing is u dot gradient omega, and then c d z d s, and of course you also need to consider this boundary part. But here, for the purpose of the simplicity, let's just pretend that on the right hand side you only have this nonlinear term because that's the main enemy. So let's pretend like we're just dealing with this, we don't ignore this initial data term, ignore the boundary term. Let's just look at this. And here, I need to simplify it more, actually. So here, let's just consider omega is equal to this 0 to t, 0 to infinity, g t minus s, y minus z. And this velocity is one derivative less than this omega. So you can just think this as lambda inverse omega. That's you can think it like that's lambda is one derivative, right? So one derivative inverse is like you get one derivative less, and then this gradient omega. So here. And then you do the energy estimate. Let's say you have this x mu norm is equal to, let's see, the energy estimate. You work out, you have like it's from 0 to t, and then there's, actually I want to consider the second derivative. If you consider the second derivative, let's say here you have like the second derivative of the first term, you get gradient omega x mu norm. And the second term for this one, what you get is like gradient d squared omega x mu norm, and then ds, right? Okay, I do not want to, so I just okay, I just briefly finish this. So here this, do not worry, there's just one more line, and then we are done. So here this, then it's according to the analyticity recurrence. So what we have is gradient omega x mu norm, and then you have like 1 plus mu naught, 1 over mu naught minus mu minus gamma t, and then it's, you have this one derivative recovery, so you can factor this, but you get rid of this derivative, right? So here, and remember this x norm. If you look at this x norm, there's this weight here. So if you go to x mu norm to x norm, you get an actual power of this. So it's 1 plus half plus alpha. Then, but you go to like x norm, not x mu norm anymore. It's x norm ds, and this guy is less than gradient omega x. X omega x norm. So it's less than 0 to t. Then I guess like I do not want to write this anymore. So it's x norm squared. Right, this x norm, and then this, there's no derivative here. So this, because we go to x norm, the derivative is already included in the x norm. So here there's omega x norm squared, and then you integrate just this power. What you get is just mu naught minus mu minus gamma t to the power of half plus alpha. And that's exactly the weight, this guy, right? So if you multiply everything to the left side, you put this guy to the left side, that's on the left side, you get like omega x norm is less than omega x norm squared divided by some big constant gamma. And if you choose your constant gamma big enough, this is doable. So from here you get like this norm is preserved, and from the from this you can gain the inviscid limit problem like easily. So okay, thanks. I go a little bit over the time. So. Thank you very much. Thank you.